Hello everybody, my name is Praks. I'm coming from Finland, Aalto University, and first of all I would like to thank and acknowledge my co-authors Matti Vaija, Jaakko Seppänen, Rafal Mlodrzewski, Anssi Hakkarainen, Benjik, Sami and Janne Lahtinen, and we are all coming from Aalto University or Hard Technologies from Finland. I'm telling you about an idea we are working at the moment in Finland. This is frequency interference, radio frequency interference measurements, and I'm going to give you a small overview. What is this radio frequency interference problem, how it is mitigated, and what we can do with CubeSats. First of all, let's go to a much bigger mission. This is European Space Agency Earth Explorer mission. It's called SMOS. Soil moisture and ocean salinity mission. Our university and our institute was part of building this satellite, and we're still making measurements with very similar instrument with our airplane. And this mission was launched 2010, and it had a problem. And this problem is radio frequency interference. It's a radiometer which is measuring a natural emission of Earth, oceans and land areas, and forms this type of maps telling about soil moisture and ocean salinity. These both parameters are very important for mapping global change, dynamics in oceans, moisture balance, and how it affects atmospheric properties. The instrument works at the L band, which is 1.4 gigahertz, which is protected and reserved for passive measurements only, and it is reserved for mainly for radio astronomy, because there is one important oxygen absorption line in this area. However, after SMOS satellite was launched, it appeared that on this protected radio band there is a lot of traffic going on. And in reality, there is a very strong corruption of these frequencies, a lot of different types and different kind of sources constantly emitting radio frequencies on this very narrow 27 megahertz band. And it was for two first years of SMOS mission was a constant struggle with this kind of RFI sources. It was for some areas not even possible to make the maps and get the scientific data. And as we know, we are going to have more and more remote sensing satellites for Earth observation, and also more tighter and tighter use of radio frequency spectrum. So it's becoming more pronounced problem every year. So, for example, this is a picture of soil moisture made 2012 from ascending orbit, and you see there is no data on Europe. And the problem was that from Europe on ascending data and distant antenna directions, it was so many different illegal sources on this area that it was just not possible to make a measurement. Now, SMOS satellite is actually the only satellite which is constantly making also radio frequency interference maps on this area, on L band, 1.4 gigahertz. And from these maps we see different kind of areas which have strong sources. There's typically abundant old systems which are working on wrong frequencies, or airborne radars which are leading to a wrong frequency. Very different kind of problems. A lot of those problems have been mitigated, but not all. There are more missions coming. Just few names: Biomass mission, which is the Earth Explorer mission, again from European Space Agency. It has a radar, but this radar has very low frequency for a radar, half a gigahertz, and bandwidth which is only 6 megahertz. And there is a serious concern that also this bandwidth is corrupted with radio frequency interference. There is a SMAP mission launched very soon, working on 1.2 and 1.4 gigahertz area. And also, this is unknown how much radio frequency interference we have in these areas. And you don't need to have a big transmission in this region. Half a Kelvin and you totally ruin, for example, the salinity measurements. 1 Kelvin and you are seriously affecting your soil moisture measurements. And that's why even small sources like Wi-Fi router, which is working in a wrong frequency, is enough to totally spoil your measurements. So there's a couple of more names of the satellites and instruments, and you can see that these Earth observation satellites are mostly working L-band, C-band, up to V-band, but let's say the most important area is from 1 gigahertz to 25 gigahertz mostly. So, how to solve this problem? Solving the problem actually started with SMOS satellite mission. And first of all, you have to quantify the problem somehow. You have to measure how much unwanted signal and noise we have on these frequency bands we are interested in. Then we of course have to deal with cause. Maybe there is a possibility to switch off these illegal transmitters. And also mitigate the consequences. There is several different possibilities to extend the integration time, to select non-affected areas from the integration and integrate only the good areas of the frequency band or the time scale. And then you can get out the functional system, which is SMOS satellite soil moisture measurement actually at the moment is. However, I believe that CubeSats can actually contribute quite a bit in quantifying the problem, measuring the RFI before the actual big missions are launched. Some of the requirements, what we should do, we want to know radio frequency interference frequency distribution, we want to know time distribution and statistics, and also power distribution, and then spatial distribution. From what areas we are getting these signals. If we want to do it with a CubeSat mission, then of course we face very severe power consumption restrictions, antenna size is limited, data link capacity is normally very limited, and also the revisit time and coverage can be limited depending on the orbit we are able to get or to get the piggyback launched. So current radio frequency detection algorithms are quite simple. First of all, they are based on just detecting the anomalous high amplitude of the signal, or then a bit more advanced algorithms are measuring the probability distribution function of the power and measuring its different parameters, for example kurtosis, and detecting with this statistical parameters, selecting the areas which are not normal and excluding them. And also polarization is one of the possibilities, because very many artificial signals like radio signals are strongly polarized, as natural signals are usually not. And mitigation, as I said already, can have different strategies, but you can get rid of these signals if you know where they are and what kind of nature they have, and you can maybe integrate around the good, about the good parts of the signal and leave out the bad parts of the signal. So we should measure in two directions, a frequency direction and time direction. And of course, the better time resolution and frequency resolution we can get, the better is the result, the better map, the better understanding of the situation is. However, we can do a lot of statistics already with a quite low time resolution and quite low frequency resolution. We can get already some information about the areas which are affected with a certain type of radio frequency interference and take actions. And if we want to use this for a certain type of mission, then of course the parent mission will define the real requirements, what we want to do, what we want to measure, and how exactly. So this kind of radio frequency interference detector is just a simple radiometer system, and with current technology you can have quite good filters, amplifiers, and feed everything to FPGA, where you can analyze even the same wavelet-based systems can be used, but you can analyze your signal and select the corrected areas of the signal and mark them down. We actually have already an existing prototype which is developed by Arctic Technologies in Finland, and already this prototype can be fitted into a CubeSat. It works on SMOS frequency 1.4 gigahertz. It has 100 megahertz of bandwidth, and it works only with one polarization at the moment. But there is already a new version coming with a double of bandwidth and two polarizations, which already giving much more opportunities for detecting a real radio frequency interference. For CubeSat, of course, the big limitation is antenna, because we cannot have very big antenna, so there is two options, isotropic antenna, maybe dipole antenna or several dipoles, and in this case you cannot get very much spatial resolution, or you cannot get almost no spatial resolution, but as your satellite is orbiting the Earth, you still can get the statistics about what orbits, what areas are affected by radio frequency interference, and this type of isotropic antennas is most probably the only possibility to investigate radio frequency interference lower than L-band frequencies, lower than 1 gigahertz frequencies. You also can have patch antennas, and with a bit better gain and directivity. However, in these cases you also already need an attitude control, and this makes your system much more complex. And of course, with real bigger antennas, it's all actually possible to think even about the parabolic antennas, and thinking about, for example, spinning, rotating satellite solutions, where you can map quite good resolution, ground resolution, for example, with this kind of satellite, which actually has been already flown. About orbit and coverage, of course, you can start off with a very typical polar orbit for easy access. You can get a launch for this kind of orbits quite easily, and you can get statistics worldwide about radio frequency interference problems. However, if you want to really get a good coverage, you should have more advanced systems. Power constraints are quite severe for CubeSats. However, the prototype is working at 20 watts, and this can be scaled down because most of the power is consumed by the digital processing of the data. And if we are leaving off a bit of the processing on the signal side, having smaller resolutions in frequency and time scale, we can reach the levels of about 10 watts, which is typical for a CubeSat, and for example a 3U CubeSat, it can be already feasible. So data collection strategy is also an important point, and for example with onboard data processing you can do a lot of tricks already for your link transmission optimization, and you can get down the data, statistics data about the radio frequency interference even with a single ground station. However, of course, if you have more ground stations and certain areas where you can measure more, then you can adapt your data collection strategy. So we are coming to conclusions. Radio frequency interference is a growing problem for Earth observation microwave radiometer satellites, and the most important areas which are affected and interesting for this type of satellite is 1.2 gigahertz to 25 gigahertz, and unfortunately there is no global data available about what kind of radio environment we have on these frequency bands. And We think that a simple CubeSat-based system can be used for mapping radio frequency interference statistics worldwide, globally, and this type of missions can be used and should be used as a precursor missions for a really big radiometer missions, for example, like SMAP, or for example, for a radar missions like biomass. And we are strongly recommending that this option should be considered before this very expensive big radiometer mission is launched to unknown radio environment. It should be studied first. So, just a couple of words about AL1 CubeSat, which I'm also representing here. We are in integration and qualification phase and looking for launch. But this will be covered later on by Tuomas Tikka, who is presenting on Wednesday. So, thank you very much.
Thank you again for the presentation. Any question for the speaker? Yeah.
Thank you very much. How do you deal with these illegal radio frequency sources in practice?
Yeah, there is. It's a very complex issue. Of course, the biggest problem is countries which are not really cooperating. But in many cases, you actually can go and switch them off if you know exactly where they are. For example, we have been switching off a lot of illegal sources from Spain, from Europe, from Finland, for a SMOS mission. And nowadays, the area in this L-band region is much more cleaner, so SMOS satellite is delivering really useful data.
So you call the police, the Finnish police?
There is, of course, officials in every country who are actually dealing with radio frequency allocations, and they are not able to cover and measure all the spectrum all the time. But if you point out that there is a problem, they are very willing to go and switch it off.
Thanks.
Any other question? Okay, so thank you very much for the presentation.